Okay, Hadi.
Hi, good morning, good afternoon, good evening, everyone. Welcome to the Geoscience and Geoenergy webinar of 10th of June 2021. So quickly, we are midway through the year. Hope everything is well with you and your loved ones. Today, Sebastian and myself are pleased and delighted to host our dear colleague and friend Bo Gu from University of Arizona. Bo is an assistant professor in the Department of Hydrology and Atmospheric Sciences at the University of Arizona in the US. His research focuses on the fundamental physics and mathematical and computational modeling of fluid flow and transport in permeable geological materials, motivated by energy and environmental problems, including shale gas oil production, geological carbon storage, and fate and transport of emergent contaminants in soil and groundwater. Prior to joining the University of Arizona, Bo was a postdoc in the Department of Energy Resources Engineering at Stanford University. Bo holds a BS, Bachelor of Science, with highest honor in hydraulic engineering from Tsinghua University, and an MA and a PhD in civil and environmental engineering from Princeton University. I would like to also ask the audience, please go and visit his Google Scholar page and get in touch with him for the joint works and mutual interest that you have on the fundamental aspects of understanding the complexities and beauties of multiphase flow and mechanics in porous media. It's a great pleasure and honor, Bo, to host you this week. Thank you for graciously accepting our invitation. To the audience, please note, Bo's lecture would last for about half an hour, followed by questions and discussions like always. Please do type your questions in the chat box. Sebastian will chair the discussion session like always. Do not wait until the end of the presentation to ask your questions. Please do post them whenever you feel appropriate. Your question may trigger other colleagues' questions as well. And so we will get plenty ones to go through and have a lively discussion with Bo. Thanks once more, Bo. We are all looking forward to hearing your talk.
All right. So first of all, really thank you, Hadi, for the kind introduction, and I would really like to thank both of you for the for hosting me as part of the great Geoscience and Geoenergy webinar series. It's really a great opportunity and pleasure to share some of the work that we have done in the past several years after I've joined the University of Arizona. So just a little bit history behind this line of work. As some of you may know, my PhD work was actually about a development of analytical and numerical multi-scale models for quantifying large-scale geological CO2 storage problems. So I became interested in pore-scale physics during my postdoc, where I was trying to understand, the complex single-phase gas transport in shale rocks, in narrow porous shale rocks. So this work that I'm going to talk about today is related to, but goes much beyond my postdoc work, where we now wanted to understand the compositional two-phase flow, and more importantly, the nano-confined phase behavior in shale rocks. All right, so this work was primarily done by my student, Shidian Chen, as the first author. And we also collaborated closely with Jiamin Jiang from Chevron, and also Chaozhong Qin, who used to be in Utrecht and TU Eindhoven, and he's now back in China at Chongqing University. Okay, so let me see, how can I move the slides? All right, so let's begin by take a step back and look at how the energy landscape looks like. So this graph shows the share of the various kinds of energy resources, including renewables, nuclear, oil, natural gas, and coal in the United States from 1950s to 2020. So we can make a couple of interesting observations. First of all, we see that renewables are gradually picking up. However, the fossil fuels remain to be the major energy resource. All right. The second observation is that probably most of us would agree that the fossil fuels will have to decline over time in the future and be replaced by renewables for the better of our Earth. But we have to also recognize that not all fossil fuels are equal. For example, we see a clear decline in coal, but not much so for oil and natural gas, especially natural gas. Okay. In fact, natural gas keeps growing in the past several years. Even during COVID last year, it remains largely unchanged. So it accounts for about 34% of the total energy resources. And one thing to mention is that among all of the natural gas, 78% of them now it comes from shale gas. I mean the gas produced from unconventional shale formations. All right. So I think it's all of this indicates that arguably natural gas and shale gas as the cleaner fossil fuel will likely remain as a major source of energy until the renewables ramp up to really be able to meet the large scale energy demand. All right. So producing hydrocarbon from shale formations is much more difficult than producing oil and gas from conventional reservoirs. So it has only become possible about 15 years ago when two new technologies were developed that include horizontal drilling. So drill a well and then turn it horizontally, and then hydraulic fracturing using high pressure fluids to generate fractures to increase contact areas, enhance production. Okay, so over the years, significant advancements have been made to especially in engineering and operation. However, technical problems still remain to improve the efficiency of production and also reduce environmental footprint. For those of us who are interested in porous media research, the challenges would include better quantitative understanding of the strongly coupled flow, transport, and geomechanics. Okay, complex geochemical processes due to the interaction between hydraulic fracturing fluids, and the shale rocks. And finally, the complex transport and phase change dynamics in nanoporous shale matrix when pressure and temperature are perturbed, for example, during production. Okay, so this last item is what my group is interested in and will be the focus of the talk today. All right, so before we dive into the nano-confined phase behavior, I would like to walk you through some basic thermodynamics, because we'll be using some of these concepts a lot during the presentation. All right, so suppose that we would like to measure the phase behavior of a fluid mixture. What do we do? Okay, we often put them into a PVD cell and then change the temperature and pressure and see how the status of the fluids. Okay, for example, here we put a liquid mixture into a PVD cell and then we decrease the pressure gradually, and then the liquid mixture becomes two phases and then eventually becomes a gas phase. And this experiment is done for a given temperature. Okay, so if we repeat this experiment multiple times at different temperatures, we get a bunch of data points on the pressure temperature diagram. And if we connect the data points that indicates the transition from the liquid phase to two fluid phases, and then from the two fluid phases to the gas phase, we get a so-called phase envelope. And this phase envelope can be used to describe the phase behavior of a fluid mixture. Okay, so essentially, within this phase envelope, let me put a laser point. Okay, so within this phase envelope, there are two fluid phases coexist, and outside this phase envelope, it's either liquid phase or the gas phase. All right. So one thing to mention is that this type of phase envelope is oftentimes referred to as bulk phase envelope, because it reflects purely the property of the fluids and does not depend on the container in which it's measured. Now, so for conventional oil and gas reservoirs, the hydrocarbon often reside in either sandstone or carbonate, whose pore size is on the order, usually on the order of micrometers. And if we were to measure the phase behavior of fluids, we will get something identical, or the same as the bulk phase behavior. All right. Now, what's interesting about the shale rocks is that they have pore structures that are super tiny, often on the order of nanometers. And if we were to measure the phase behavior in these nanopores, the phase behavior would significantly deviate from that of the bulk phase. And this has been, demonstrated by nanofluid experiments and molecular level simulations. And the deviation has to do with the size of the pores, and then interaction between the fluids and the solid water, etc. Okay. Now, the question is, what are the specific mechanisms that are responsible for this deviation? Okay, so these prior nanofluid experiments and molecular level simulations have revealed that there are two mechanisms that drive this deviation. The first is capillary pressure. So when two fluids coexist in a pore, they form a fluid-fluid interface, and the radius of the radius of the curvature of the fluid interface can become quite small when the pore is on the nanometers, on the order of nanometers. As we know, the capillary pressure is inversely proportional to the radius of the curvature, so the capillary pressure can become quite large as the pore goes to nanometers. And so this will introduce a strong pressure difference between the two fluid phases, and that can affect the phase behavior. Okay. The other factor is due to competitive absorption, and the idea is that these tiny pores, right? The specific surface area is quite large, and what's interesting is that the pore walls often preferentially absorb the heavier components. So what happens is that because of this absorption, the bulk fluids becomes lighter. Okay, and this subsequently would change the phase behavior of the fluids in the pore. All right. Okay, so all of this fundamental understanding of the phase behavior physics is all nice, but as engineers, we always would like to connect these basic physical processes to the reservoir scale. Okay, to the reservoir scale. So that leads to the overarching question that drives our research, which is, how do molecular level physics that we have talked about just now affect, the processes that we see at reservoirs. Okay, and reservoirs. And of course, we recognize that this question is a big and challenging question. So we will actually ask two more specific questions and show that the approach that we use to address them, and to demonstrate the possibility of tackling this big question, at least under certain conditions. Okay. So the first question that we ask is, how does the nano-confined phase behavior manifest in multi-scale pore networks? Okay, so if we can do this, right, then we can connect this to, hopefully to a core scale, and then we can implement this into reservoir simulators. All right, and we recognize that there are multiple many orders of magnitude between the scale of a molecule and a pore to the reservoir. Okay, so the idea of this question is behind this question is that as we discussed earlier, right, the nano confinement, the strength of the nano confinement is size dependent. Okay, size dependent. So we would expect the nano confinement effect to be stronger in the smaller pores. Okay, in the smaller pores. So if you look at two different pores, they would have different phase envelope. All right. So now for a multi-scale pore network that consists of pores with different sizes and different geometry. Now the question is, what would the overall phase envelope or like phase behavior be for such a multi-scale pore network? Okay, so to address this question, we develop an upscaling framework for to connect the single pore phase behavior to a network of pores, and this will be the first part, the focus of the first part of the talk. Okay, so in the next few slides, I'm going to present some key ingredients of this upscaling framework. The first step is to try to represent the pore structures. Okay, so the way that we did it is that we use a network extraction algorithm to extract from digitized, three-dimensional images of rocks, and so that we can get a sort of an idealized pore structure that reflects some of the important information of the original pore structure. So there are multiple ways of assigning the volumes to pore bodies and pore throats. Okay, so I forgot to mention that. So these networks, just a quick sort of introduction. These networks, are consists of interconnected pore bodies and pore throats. Okay, and hopefully that can represent some of the key information of the original structure. And so, as you can imagine, after we extract the network, there are multiple ways of assigning the volume of the original network to the pore bodies or pore throats. So here we use the approach that we assign all of the volume to the pore bodies and assume that the pore throats are volumeless, okay, volumeless, so that we can focus on the phase behavior calculations in the pore bodies only. So ideally, this extracted pore network would replicate the pore size distribution, pore connectivity, volume, surface area, shape factors, etc. of the original structure. Now, after we have represented the pore structures, we need to think about how we can represent the nano-confined phase behavior processes in this network. Okay, it's obvious that we are not able to afford the molecular level simulations because these networks can have millions of pores. Okay, it's not possible. It's not feasible computationally. So we sort of have to find a model, sort of in an average sense, that can represent the phase behavior in each pore body, but without resolving the molecules and explicitly discretizing the pores. So when we started to work on this problem in 2018, we saw a very nice paper from Denmark Technical University, where they presented a phase equilibrium model that accounts for capillary pressure and the absorption that we talked about earlier on the phase behavior in a cylindrical nanotube. Okay, nanotube. And this paper was the authors include Sandova, Yan, Mitchelson, and Stenby. Okay, so it's a very, very nice paper that was almost exactly what we were looking for. All right, so here's what they did. So they consider a cylindrical capillary tube, and so because it's a cylindrical capillary tube, so the capillary pressure can be easily calculated based on the Young-Laplace equation. Right, the capillary pressure would be inversely proportional to the radius of the tube. Okay. Now, they also assume that there's adsorbed phase at the pore wall, and this adsorbed phase can be modeled by some type of adsorption model, and they used the multiple component Long-Muir model for simplicity. And so once they have this capillary pressure represented and this adsorption model represented, they can then plug in this into the standard phase equilibrium model, and the computational structure would be very similar to the standard phase equilibrium model that has been often used for reservoir simulations. With two differences. The first is that now the phase pressures are different. Okay, they differ by a capillary pressure, and this capillary pressure sometimes can be very large. Okay, so that has to be taken into account when computing the chemical potential of the component in the liquid and gas phase. The other difference is that now the adsorbed phase is also part of the phase equilibrium calculation, and this adsorbed phase is linked to the bulk phase through this adsorption model. Okay, so this is now this phase equilibrium formulation, really sort of provides a base or a foundation for us to think about our problem. Okay, think about our problem. However, recall that the pore structures that we have can have arbitrary geometries. Okay, for example, it can be a tube with square cross section or triangular cross section, etc. Okay, so we would have to extend this formulation to account for arbitrary geometries in tubes. For example, let's look at a tube with a square cross section. Okay, and for a given fluid saturation, because we assume equilibrium inside this pore, okay, we can figure out the geometric configuration of the fluids and then compute the radius of the curvature. All right, so this would allow us to compute the capillary pressure. Okay, so the capillary pressure now would be a function of saturation, and as opposed to just a function of the radius of the tube in the cylindrical tube case. So this adds a little bit complexity, but it's not too much in the sense that now we put this capillary pressure as a function of saturation into this phase equilibrium formulation and solve everything in a Newton loop. Okay. Okay. So with this, we now have a phase equilibrium model for each single pore that accounts for the impact of capillary pressure and adsorption. Okay, and this is reflects the size and geometry of the pore. All right. So now we need to think about how we can upscale this single pore phase equilibrium model to a network of pores. Okay, so just like in many upscaling procedures, we sort of have to assume some type of equilibrium, and that's what we did. So we assume thermodynamic equilibrium in all of the pores across the entire network. Okay, across the entire network. So this means that, for example, the phase pressure, the chemical potential, and composition in each pore is the same across the entire network. Okay, and this is this is a strong assumption, but it allows us to really do algebraic averaging of all of the individual pores to compute to define and compute macroscopic phase equilibrium variables for the entire network. All right, so in essence, we get a macroscopic phase equilibrium model, a closed that has a closure. And it's only written in terms of the macroscopically defined variables. Okay, and another way to think about this is that this network scale phase equilibrium model is to some extent a phase equilibrium model for an apparent pore. Okay, for an apparent pore, and this pore, the PCS curve of this pore, the capillary pressure saturation curve of the pore and adsorption, reflects the aggregated information of the pore structure. Okay, of the pore structure. So this is an important and useful insight, because this means that the computational structure of this upscaled thermodynamic equilibrium model is identical to that of a single pore, except that now the variables are macroscopically defined. Okay. This is also practically important, because this means that we can easily plug in this phase equilibrium formulation into an existing reservoir simulator, just as the standard phase equilibrium models. Okay, of course with additional formulation for capillary pressure and adsorption, etc. Okay, so in the next few slides, I'm going to show you some results. Where we simulate the phase behavior using the extended single pore model and the upscaled network scale model. Okay, so let's first look at the simulation results of a single pore. So we consider a tube with a square cross section consists of two components, methane and butane, and here's what we would get if we simulate the bulk phase behavior. Okay, bulk phase envelope. If we assume that the pore is 100 nanometer, we get a phase envelope like this. Okay, so you can see that the phase envelope does not change much from the bulk phase behavior, which means that nano-confinement effects are not significant, at least for this 100 nanometer pore. However, if we further reduce the pore size to 10 nanometers, we see a significant deviation from the bulk phase envelope. Okay, and so in our simulation, we find that between the two factors, capillary pressure and adsorption, the adsorption is the dominant factor, okay, rather than the capillary pressure. And what happens is that because of competitive adsorption, the bulk fluids becomes lighter because more heavier components are adsorbed at the pore wall. And so this is actually consistent with the so-called stripping effect that has often reported in molecular level simulations. Okay, so stripping effect basically means that heavier components are preferentially absorbed and the bulk of fluids becomes lighter. All right, so now let's also look at some simulated simulations for using the upscaled model for pore networks. Here we consider a network that has 1 million pores, okay, 1 million pores, and following the pore size distribution on the right. So most of the pores are below 100 nanometers, okay. And to examine the impact of pore geometry, we consider two cases. The first case assumes that all of the pores are square tubes, and the contact angle is 0 for the liquid, so it's completely wet. And the second case assumes that the pores are randomly consist of square and triangular tubes, okay, and the contact angles are non-zero and they follow a normal distribution shown on the right. All right, so let's see, what the phase behavior will look like for these two networks. All right, so we can see here I'm showing the simulated phase envelope for the first case. We can see that the solid line is the phase envelope for the entire network, and the two dashed lines are the phase envelope for the smallest and largest pore in the network. Okay, so as we can see, the overall phase envelope deviates strongly from the single pore phase envelope, and the exact deviation would be dependent on the pore size distribution. Okay, and because we have the detailed model structure, we can then look into the distribution of liquid phases, the phase fluid phases and the components in the different pores. Okay, for example, here I'm showing the liquid saturation in the pores with different sizes, and we see that the liquid saturation is much greater in the pores with smaller sizes. Okay, this is understandable because the smaller pores will trap more liquid, the wetting phase. Okay, and then what's more interesting is that we can also compute the ratio between the heavier components and the lighter components in these pores, and we see a similar trend. In the smaller pores, the ratio between the heavier and lighter components is greater, and this is driven by two processes. One is what we see before. Smaller pores have more liquids. Okay, liquids has greater fraction of the heavier components, and also the smaller pores has stronger adsorption. So the adsorbed phase also have heavier components, more heavier components. All right. So all of this is saying that the pore size distribution has a significant impact on the macroscopic phase envelope, and it also controls the distribution of fluid phases and components. Now let's look at the second case where we have arbitrary pore structures and non-zero contact angle. I'm just going to put the results on top of the case one just for comparison. Okay, we can see that the phase envelope doesn't change much. Okay, it almost stays identical. So this means that geometry and wettability does not influence much of the overall phase envelope. However, if we look at the distribution of the fluid phases and components, we see a big difference. Okay, so now if you look at the liquid saturation for the same pore size, it spans a wide range. Okay, so in fact, it goes to two clusters. One of the cluster represents the pore with a square cross section, and one of the cluster represents the pore with a triangular cross section. And within the cluster, they also change because of the contact angle. Okay, because of the contact angle. And this is the same for the component distribution. So this means that although pore geometry and wettability does not change the overall macroscopic phase envelope, they do modify the fluid distribution and component distribution. All right, so just to quickly summarize the first part of the talk. So we have developed an upscaling framework for nano-confined phase behavior in multi-scale pore networks. And this upscaled model provides a workflow to derive macroscopic phase behaviors in shale rocks. And it also represents the nano-confinement effects revealed by the molecular level studies. And because the computational structure is very similar to the standard phase equilibrium model, it can be readily incorporated to reservoir scale simulator, which we plan to do. All right, so all right, it's quite neat that the upscaled model can be can allow us to sort of bring this molecular level physics to the reservoir scale. However, we have to remember that the upscaling procedure relies on a couple of key assumptions. Okay, one of them is that we have to assume thermodynamic equilibrium across the entire network. Okay, the other assumption is that the distribution of the fluids does not reflect anything about the displacement process. And these assumptions may or may not be true under reservoir conditions. So to examine these conditions under which this upscaling framework is valid, we ask the following question, which is how does nano-confined phase behavior interact with two-phase flow dynamics in multi-scale pore networks? And to address this question, we develop a computational framework that couples dynamic two-phase flow and nano-confined phase behavior in a network of pores. Okay. So the task is quite big that we had to pursue it in two steps. In the first step, we will develop a fully implicit dynamic pore network model without accounting for the phase behaviors. And in fact, we'll even go simpler. We'll assume the fluids are immiscible and incompressible. Okay, just focus on the framework. So in the first part, right, we already have the network extracted, and we also have the configuration of fluids inside each pore. Now, for dynamic pore network models, the most important part is the displacement of fluids between pores. Okay, and this include drainage, where non-wetting phase displaces wetting phase. In our case, gas displaces liquid, and this would involve pore throat opening events, and imbibition, where liquid displaces gas, and would involve pore throat snap off events, etc. Okay, so one thing to mention is that in our case, we assign all of the volumes to the pore body. So each pore body would have, in our case, when two fluids exist, we would have two pressures, and this is the so-called two-pressure formulation for dynamic pore network model. If we put everything together, we get a mass balance equation for each of the fluid phases. Okay, basically the mass change of the fluids of the phase with the flux coming in and out through labyrinth pores. All right, augmented by a bunch of algebraic equations, including the saturation sum up to 1, capillary pressure, and relative permeability as a function of saturation. Okay, so if you look at these equations, they are almost identical to what you would see in for reservoir simulations, but with a couple of key differences. One of them is that for this dynamic pore network models, the relative permeability can suddenly change from non-zero to 0, or from zero to non-zero, because of the pore opening and snap-off events. And that introduces a lot of discontinuity to the system and make it hard, actually quite challenging to solve. And there are several ways of solving these equations. The prior studies, all of them assume use the so-called decoupled approach. So it sum up these two mass balance equations to form a pressure equation, and then use one of the governing equations as the equation for saturation. So the pressure equation and saturation are solved sequentially without iteration. And so when the pressure is solved implicitly, saturation is solved explicitly. It leads to the so-called impasse algorithm. And when the saturation is also solved implicitly, it leads to the semi-implicit algorithm. Okay, so we have done detailed comparison and benchmarks for all of the three methods. Well, okay. So I forgot to mention that we use a different approach. We decided to solve all of the equations fully implicitly, because we anticipate that for our problem, where we have strongly coupled flow, transport, and phase change dynamics, the decoupled way of solving the equations may not work for our problem. Okay, so in our paper, we have conducted detailed comparisons and benchmarks between all of the three methods. I will not be able to talk about the details here, except just briefly mention some of the take-home message. All right, so in the next few slides, I'm going to show you some sort of example simulations to demonstrate the applicability of the fully implicit framework for simulating some challenging flow regimes that have been reported for dynamic pore network models. So here, the first case, we consider low capillary number flow. And the way we consider we set it up is that we take a network, and that is fully saturated by the wetting phase, and we inject the non-wetting phase from the left. So if we increase the pressure in the injection point step by step, we can generate a bunch of quasi-static solutions just by using the simple invasion percolation rules. So essentially, we get a PC capillary pressure and saturation curve, and each point would correspond to a quasi-static solution. Now, if so now the way to generate a low capillary number flow situation is to start from one equilibrium solution and then run the dynamic simulation until it reaches the next equilibrium solution. So as it asymptotically approaches the next equilibrium solution, the capillary number would go to 0. Okay, the capillary number would go to 0. So we did that, and we see that the dynamic simulation can precisely land at the next equilibrium solution. Okay, which means that it is able to simulate the low capillary number flow, and we did that for all of the equilibrium points, and it again matches all of the equilibrium solutions. We did that. So the previous simulation was for the square tubes, and we also did that for cubic pores, and the results is the same. Okay. So the second scenario that we tested is to simulate displacement processes for a wide range of viscosity ratios. All right. So the setup is similar, but we ran 4 simulations that includes viscosity ratio between the injection and displaced fluid from 10 to 0.01. And we see that, depending on the viscosity ratio, we see different patterns of displacement. For m greater or equal to 1, we see piston-like displacement, and for m smaller than 1, we see fingering displacement patterns. So all of this shows that it appears that the fully implicit method is able to simulate these challenging flow regimes. Now, I would like just to briefly comment on the mass conservation error involved with when these two equations are solved in a decoupled way. So there's what we found is that when using the decoupled way of solving the equations, there may be global mass conservation errors. Okay, and there are many details behind this statement, but the idea is that when during the simulation, right, the saturation in a pore can go beyond the physical range, meaning below the residual saturation or above 1. And when that happens, and when the two equations are decoupled and solved sequentially without iteration, the only way to put it back to the physical range is to throw the mass away or add additional mass to the system. And if that happens a lot, then it can generate global mass conservation errors. Okay, and what we found is that this global mass conservation error will depend on the flow regime you simulate, and also will depend on the pore geometry. Okay, so for some situations that the mass conservation error can be large, but for some of them the mass conservation is almost negligible. Okay, so the take-home message is that if you ever want to code or you want to use some dynamic pore network models, these are some of the factors to be considered. All right, so So now we have this computational framework, a fully implicit computational framework for two-phase dynamic displacement. Now we would like to couple that with the nano-confined phase behavior that we discussed in the first part of the talk. Okay, the first step is that we have to reformulate the mass balance equations for the component. Okay, for the component. So we have the instead of the fluid phases, we have the mass change in the liquid, gas, and adsorbed phase, with the fluxes coming in and out driven by advection and diffusion. The advection flux is driven by displacement processes, and the diffusion flux is driven by a concentration gradient. And remember that for each pore body, we need to account for the capillary pressure and also solve a phase equilibrium model. And we assume that within each pore, we have a thermodynamic equilibrium, but not between pores, okay? All right, so in the next a few slides, I'm going to show you some preliminary results that we have simulated for dynamic two-phase displacement in the presence of compositional transport and phase change dynamics. Because the implementation of nano-confinement effects in the dynamic pore network model is still ongoing, so I will only show the results that couples the bulk phase behavior. Okay, bulk phase behavior. All right, so here we consider a network that is initially saturated by a liquid mixture, including C1, C5, and CO2, and then we inject a two-component gas mixture from the inlet. Okay, consists of methane and CO2. As we can imagine, when we inject this gas into gas mixture into the pore network, there may be evaporation and condensation occur at the invasion front. And here I'm showing two sets of results. I'm showing two sets of results. The left panel shows the displacement patterns when phase change is not accounted for. And the middle panel shows the displacement patterns when phase change is included, okay? And the right panel shows the change of the overall gas saturation over time corresponding to the two cases. As we can see that the displacement pattern is quite different in the presence of phase change. And this implies that the phase change has some significant impact on the displacement process. In fact, it appears that it arrests the little fingers and to become a dominant finger. Okay, so to better illustrate the impact of the phase change on the displacement patterns, we selected two snapshots corresponding to gas saturation of 0.2 and 0.3, and we see that without phase change, there are many more fingers compared to when phase change was included, and in fact, these small fingers are arrested due to the phase change process. And for the conditions that we simulate, we find that both evaporation and condensation occur at the invasion front, but the evaporation is the dominant process. Okay, is the dominant process, so that contributes to the arrest of the little fingers. So with that, I would like to conclude. So driven by the question of connecting the molecular level physics and pore level physics to reservoir scale, we have developed this upscaling framework for nano-confined phase behavior in multi-scale pore networks. Also, in addition, we have developed this dynamic pore network model that couples two-phase flow, multi-component transport, and nano-confined phase behavior to examine conditions under which this upscaling framework is valid. And so the next steps that we would like to do is to implement some of these to reservoir scale simulators, especially the upscaled phase equilibrium models. With that, I would like to thank everyone for your attention, and I'll be happy to take questions and during the discussion session.
Thank you very much, Bo, for this extremely interesting and engaging talk. So I see already plenty questions. I'm sure plenty more will come. So we are going to keep you a little bit busy today. So I hope you don't mind. So Sebastian, please.
Yeah, thank you very much, Borg, and also from my side for great talk. really interesting pore scale modeling, pore scale or nanoscale modeling, nanoscale physics that you're discussing. As Hardy said, plenty of questions, and some are quite long questions and run over several comments in the chat, so I'm trying to paraphrase them a little bit. I start with so comment/question from Zeo Jin. He says, he wonders, in terms of shale gas competitive adsorption, multi-component adsorption processes is more important than a confinement use phase behavior alteration. There's not really question that then follows up, but he wonders, is that something you're planning to investigate? How would your results change if you look at multi-component competitive adsorption, and how do you actually quantify this?
Yeah, so thanks. First of all, thanks, Jiahui, for the very interesting question. So in fact, so in the current framework, we did account for multiple component competitive adsorption with this multiple component Lamure adsorption model. But apparently that model is relatively simple, and the interaction between the molecules and pore wall can be more complex. So we actually plan to extend this simple multiple component Lamure isotherm to more complex models that can include the more complex interactions between molecules and the pore wall. So I agree that the competitive adsorption is important, and that's actually what we showed in the simulations. Though the competitive adsorption is more important than the capillary pressure impact.
Okay, thank you. We take a question from one of your old colleagues, well, past colleagues, not old, past colleagues from Princeton Times, Florian Doster. He says, "Hi Bo, nice presentation. With respect to equilibrium assumption in the nanopore network, with nanopores, etc., did you do an estimation or time scale you need to equilibrate the properties?"
Yes, so Florian, very nice to have you in the audience, and thank you for the question. So yes, actually, that's the sort of part of the purpose that we developed the dynamic pore network model. So once we have the dynamic pore network model formulation and the framework, we can now use this to test the time scale it will take to reach equilibrium for the entire network. The other way to analyze the time scale is to just do some simple scaling analysis. So because we would like to first have the computational framework in place, that's still sort of ongoing. And once we have that, we would like to do exactly the analysis that you suggested, which is to understand conditions under which the equilibrium assumption is a valid one.
Okay, thank you. Let's talk a little bit about capillary pressures. And we have a question here from Søren Pop, and he says, "Thank you for the nice presentation. The network scale model that you present in slide 11 is using capillary pressure saturation relationship. How is that obtained, derived, and do you plan to include other type of effects like hysteresis in the future?"
Okay, so the if I remember, the slide 11 is basically we have a tube with a square cross section, and the way we obtain the capillary pressure saturation curve is basically to assume that because the fluids is the liquid fluids would reside on the corners, okay, and then we can determine the geometric configuration of the fluids if we know the contact angle, and then that would allow us to geometrically compute the radius of the curvature, and that would allow us to then link the capillary pressure as a function of saturation. So it's a relatively simple model, and it does not account for hysteresis within a single pore, and also for the upscaling framework, right? It also does not account for hysteresis, because for a given saturation in the network, we assume equilibrium and we do not account for the impact of displacement process. So we would have a one-to-one correspondence between the capillary pressure and the saturation. Okay, so that's also part of the reason that we want to develop the dynamic pore network model to examine whether that assumption is a valid one or conditions under which it's a valid one. So the single pore. So just to recap, the single pore capillary pressure curve is relatively simple, and it's the ones that are commonly used in pore network model for, literature. And in the network scale, we also do not account for the hysteresis for now, but that is sort of the next step to examine whether this is a sound assumption.
Thanks, Bo. Let's talk a little bit about capillary pressures. And later, one of our frequent viewers and listeners says, thank you for the informative and interesting talk. What is the impact on the scale of the network and simulation time on the upscaled capillary pressure curves?
All right. So the upscaling framework, the computational time is almost the same as if we were to simulate the phase equilibrium model for a single pore, because everything is upscaled, right? So the computational structure is the same as if you were to compute a phase equilibrium model for a single pore, because everything is written. The equation would be identical actually, with just the variables being defined at the network scale in an average sense. So the computational time for the upscaled model would be just as fast as any single pore phase equilibrium model, and that's why we are planning to implement this into reservoir simulators, and because that would be relatively straightforward. But the dynamic pore network model, is much more computationally expensive, because first of all, it's dynamic displacement process, and second of all, we have to solve the phase behavior inside each pore body. Okay, as opposed to solve one phase equilibrium model for the entire network. So that is actually quite computationally expensive. In fact, that's also the reason we were not able to present the results with nano-confinement effects in the dynamic pore normal, because it's still running in cluster. Okay.
Thank you, Bo. Continue with staying on the pore scale topic for a moment. Really interesting question, I think, from Yuan Wang, again, one of our regular viewers. Two-part question. He says, hi, Bo, thanks for the interesting talk. I'm wondering, have you investigated the impacts of connectivity on the overall phase behavior? For example, if two samples with the same pore size distribution but different connections, would you expect the resulting phase envelope to be similar? How about the RV size here?
That's an excellent question. So for now, the upscaling framework does not account for that. Basically for now, as long as we know the pore size and geometry, then that determines the upscaled phase equilibrium behavior. However, we really think that the connectivity would have an impact on the overall phase behavior, because that would induce different displacement patterns. Okay, and that can be investigated with this dynamic pore network model. Okay, so this is actually one of the two assumptions that I mentioned that the upscaling framework makes, and hopefully we will be able to investigate that with this dynamic pore network model coupling the phase behavior formulations.
We talked quite a bit about sort of things that you want to still implement into your framework, and another set of additional follow-up questions came about. So Thomas Nagel says, hi, Bo, very nice. Could you say a few words, please, about what role thermal effects might play when we consider adsorption enthalpies in nanoporous media, in addition to the usual bulk latent heat?
Yeah, so Thomas, very nice to see you, and very nice to have you in the audience, and thank you for your interest. So we have not accounted for that because for now we assume everything is isothermal. The phase equilibrium calculations, everything is isothermal, but that could be important in the reservoir because temperatures can change, in different ranges. So that is an important. I think it's an important point. But for now, we're not able to really account for that because that then will increase the complexity of the model. But hopefully, in the future, we'll be able to at least sort of see something about how the non-isothermal effects would affect the results that we see.
And Sadeep, sorry, I need to bring the question up. Sadeep Pavuluri from Harvard PhD. Hi, Sadeep, good to see you online. Says also very nice work. Or do you plan to investigate the role of films? Does play a significant role at the nanoscale?
So we have not thought too much about that. And I think that'll be actually quite interesting, because if you have the films, then most of the solid, if the solid surface is wet to the liquid, most of the solid surface would be covered by the liquid films, and that may have some significant impact on the absorption processes. So we have not really thought deeply about that, but that'll be something to think about, actually. Thanks.
So there's some possible collaboration coming along between Saidib and Bo. Saidib, who actually happened to do his PhD with Florian, so we can close that loop here. There's some questions coming in. We still have some time around geochemistry, and I put both questions to you because they sort of tackle approach the same point. So first, Stefan Berg asks, how about using something like Reactor that remembers previous phase equilibrium calculations in terms of chemistry? And perhaps related to this later, second question is, do you have plans to add geochemistry reactive transport, which you could model with something like Reactor or GEMS in your dynamic system?
Yeah, so first of all, I'm not a geochemist. I don't know much about geochemistry. I'm starting to pick up some of the geochemistry by hanging out with some of my colleagues here. So all of these are, I think, very interesting problems. But for now, we really would like to understand the impact of nano-confined phase behavior and how we can upscale that. Okay, so this is already a very difficult problem. So once we have this figured out, we would be definitely interested to extend this to look at other processes like geochemical processes, as you suggested. So yeah, it'll be interesting to collaborate in the future once we get this problem figured out.
And related to Stefan's question, so do you think a tool like Reactor, coupling this to your framework, could help you? Because Reactor, according to Stefan, can remember previous phase equilibrium calculations?
So I'm not familiar with that Reactor. Is that an open source code, or?
Yeah, that's an open source code from memory serves me right, that Alan Leal at ETH Zurich has developed. So
interesting. So we have not explored that. I mean, that'll be interesting because especially the dynamic parameter model is quite computationally expensive, and we would like to figure out ways to reduce the computation, if possible. Yeah, so I'll look into that. Thanks.
But what you're mentioning, Bo, is that this phase behavior calculations also take major simulation time and not just transport and flow.
Exactly.
And then you could benefit from advancements in phase behavior calculations.
Exactly.
Okay.
Yeah, because we have to do the phase equilibrium calculation in each pore.
Exactly. Yeah, sure. But you are scalable because it's pretty local, and you can just simply
we can parallelize it. Yeah,
exactly.
It's independent.
So we had very early on, actually, before you started, there was a question from a series of comments from Jahan Karimi Begani. I hope I pronounced that correctly. Who they were more to production related and sand production or confined productions in unconventional reservoirs. So just of trying to paraphrase his questions, is there anything in terms of your modeling approach that in the future, you could be looking at also fines migration in modeling in nanopores, if that is a problem in shale gas production?
Yeah, I think migration of fine particles would be definitely relevant for the fractures, especially the microfractures and the hydraulic fractures. For as of now, we mostly focus on the shale matrix, and the pores are super small, so we have not really considered that. But I think that'll be an interesting question to look at for fine particle transport in fracture networks.
So definitely a few years worth of research and some interesting collaborations coming up.
Ideas from the questions. Thank you.
Good. So, Bo, thank you very much again. Our time is up. My time is up here for great talk, for taking the time to give the presentation and answer all the questions in detail. Thank you to our audience, as always, for a series of really, really good, interesting questions that stimulate some interesting discussions and opportunities for future collaboration, which is fantastic to see. And with that, over to Hadi for some final announcement about next week's speaker.
Yes, thanks very much. The next week's speaker, 17th of June speaker, is Professor Aaron Cahill from Heriot-Watt University. Aaron will speak about legacy wells and their integrity. A threat to net zero. Are they a threat? If you want to know, just join our next week Geoscience and Geoenergy webinar. But until then, make sure to stay happy and healthy and tuned into our channel. All three are important. So we see you all again next week, again with another talk. Thanks a lot, Bo. It was great to see you live, but also very good and very stimulating and energetic presentation and lecture as well. Thanks.
Yeah, thank you both. Thank you, everyone. Bye-bye.
Thank you very much.